Okay guys, so here today to talk to you some more about some key ideas about simple machines, and then also to work through an example problem of some calculations with simple machines. So the number one thing that you need to remember, and the most important idea with simple machines, is that a simple machine basically tries to make work easier for us to do. So the amount of work that the machine does and the amount of work that you do are essentially, ideally, going to be the same. Now, in reality, all machines encounter friction. And so the amount of work that you put in to the machine and the amount of work that you get out are not exactly the same. But they're usually close enough that we can assume that they are basically the same. And sometimes we'll talk about when they're not. All right, but ideally, the idea is the work that you put in as the user of the machine is equal to the work that the machine gives you. All right, so if we're talking about a pulley, for example, you're going to do work when you pull down on the pulley rope. All right, the machine's going to do work by lifting the object up. So the machine lifts the load, you pull down on the rope and do work that way. Now, if you remember, work is F, the force, times D, the distance, times the cosine of the angle. But when we're talking about machines specifically, we can actually reduce that to just force times distance. We don't have to worry about the cosine. And the reason for that is, if you think about it, like the pulley is always going to lift the object upwards in the direction that the object is moving. So the direction of motion and the direction of the force are aligned. So for that reason, we don't have to worry about dealing with the cosine when talking about the machines. So if we're saying that the work the user does, the input work, is equal to the work that the machine does, the output work, then we can express that like this. Force in times distance in, that's the work, is equal to force out times distance out. That would be the work by the machine. Okay? So that's a key idea, and that's going to allow us to figure out how much force or how much distance, input or output, by using that equation. Okay, we also want to talk about mechanical advantage. So just very basically, guys, mechanical advantage is a way of measuring and comparing how strong is the machine compared to how strong you are. All right, if you've already done some of the pulley lab, you kind of saw this where as you added more string and more pulley wheels to the machine, you didn't have to pull very hard to be able to lift that object up. All right, so the machine is obviously exerting a big force to lift the object up. You're not having to pull down with a big force. You don't have to pull as hard. So it's giving you what we call a mechanical advantage. Okay, so it measures how strong the machine is compared to how strong the user is in terms of force. Okay, and there are two different ways that we can calculate that, depending on whether we're talking about theoretical or ideal mechanical advantage versus actual mechanical advantage. Okay, so if we're talking about the ideal mechanical advantage, that would be if there were no friction or any other resistive forces, the ideal mechanical advantage is equal to the input distance divided by the output distance. So it's a ratio of those two things to divide. Okay, if we're looking for the actual mechanical advantage, and I'll just scroll a little bit here. If we're looking for the actual mechanical advantage, that's going to be, if there is friction and such, it'll take the output force and divide by the input force. And that's going to allow us to calculate its actual mechanical advantage. All right, so let's take a look at an example problem here. So the example problem says, a pulley system requires the user to pull the rope with 50 newtons of force and pull 1.0 meters of rope in order to lift an object 0.4 meters. A says, what is the output force of the machine? And B, what is the machine's ideal mechanical advantage? Okay, so it's very important when we're solving these kinds of problems. The very first thing you want to be thinking about is, what is the user doing and what is the machine doing? All right, because what the user does is what we call input. And what the machine does is what we get out. That's our output. All right, so when we look at this, get our pen ready here. The user is pulling with 50 newtons of force. So that's the input force. We'll call that F in. The user has to pull 1 meter of rope. That's the input distance, E in. Okay? And the pulley lifts the object 0.4 meters. This is the output distance. Call that D out. The question's asking, what's the output force? So that's F out. And what is the machine's ideal mechanical advantage? That's I N A. Okay? So you'll notice we know the input force and the input distance, and we know the output distance. So we know the work in and the work out are ideally the same. So I'm going to say F in times distance in equals F out times distance out. F in is 50 newtons. Distance in is 1.0 meters. F out, I don't know, so I'm just going to rewrite that, F out. And then D out is 0.4 meters. So I have 50 times 1 equals F times 0.4. I'm going to divide both sides by 0.4. And same thing over here. And if I do 50 times 1 divided by 0.4, I get F out is 125 newtons. So the user only has to exert 50 newtons of force, and they get 125 newtons out. So it's giving us a mechanical advantage. All right, and part B actually asks us, what is the ideal mechanical advantage? All right, so when we do that, the ideal mechanical advantage is going to be distance in divided by distance out. So D in divided by D out. So in that case, D in is 1.0 meters, and D out is 0.4 meters. So if we divide those two, we get a mechanical advantage of 2.5. So that means, and you notice too that the units cancel out here. Meters over meters. This is just a number. It doesn't have units. It's a ratio. So that means that the machine is 2.5 times stronger than the user. It exerts 2.5 times the force that the user puts into it. All right, so that's a good example of a practice problem using simple machines.